It's good. It's good.
We're good?
We're good.
Oh, okay.
We're good.
All right, we're good. All right. So, we've got an audio oscillator here, and that's the speaker is right inside this tube. That's a speaker coming in, and the speaker is taped to the end of this tube, and you can hear it, and I can change the frequency as an example. Okay, so the oscilloscope is a video, a picture representation of the waveform. Whoops. And essentially, the oscilloscope has two components to it. There's a time that there's an accurate clock in the oscilloscope that sweeps the electron beam. Where is the electron? That sweeps the electron beam at a very accurate time. And right now it's set for 0.5. There it is. 0.5 seconds per division, but I can change it as I increase the sweep speed. That electron beam moves faster and faster. So the horizontal axis is time. The vertical axis is voltage. And, oops. And if I can get this thing locked in, oops. Okay, but it was locked in.
It was.
It was. Now I can't get it triggered right. Ah, there we go. Okay. I think that helps. Okay, so that is the audio signal coming from the audio. That's the signal coming from the audio oscillator. It's a nice sine wave. I can change the amplitude. I can also change the frequency. And this is in channel A. Now for channel, there's a second channel here which I can bring on the screen, which is this right here. And this comes from this microphone. For instance, if I just look at this by itself, hello, this microphone goes into this amplifier right here, and it comes out of the amplifier, and the signal goes right into channel B, and I can, just look at the sound of my voice as amplified by the audio oscillator displayed on the oscilloscope. Hello, ooh, ah, so you get an idea of what your voice sounds like that. But what I'm going to do now is display both signals on the screen. Oops. Okay, so the top signal is coming from the oscillator. The bottom signal is coming from the microphone. And if you look on your lab, page 2, okay, actually, back up to page 1. Back up to page 1. On page 1, and if you look at on my screen here, basically we have a sine wave like this, and we can write this as some amplitude equals, some signal equals some amplitude, where this is the amplitude, times a sine or cosine wave, omega t plus theta. Now omega, which we've talked about before, is angular frequency, which is 2 pi times the frequency. Okay? So, and we have that right on page 2. So remember, frequency is equal to 1 over the period. So we can rewrite this as 2 pi over the period, and that's omega. Okay. So if we just ignore, let's assume this theta right here is 0. And then we say cosine 2 pi t over period. The period is the period of oscillation, or the time for one cycle. Okay, time for one cycle. As an example, if, let's say the frequency right now is, the frequency right now is almost 500, 499. Let's say 500 cycles per second. Okay, so that's the frequency. That's the same thing as hertz. So, let me turn this down. So the period is 1 over the frequency, which is 1 over 500 cycles per second. Or, if I take my calculator, 1 divided by 500 is 0.002 seconds per cycle. So this time here for 500 hertz would be 0.002 seconds. Okay? So I should be able to, for instance, I should be able to come over here to the oscilloscope, and one cycle should be, that's the same as 2 milliseconds. And if I come and look at my, so if I have this set on 1, if I have this set on 1 millisecond per division, that will be 1 cycle every 2 milliseconds. And does that look right? Yeah. We get 2 divisions, and that's 1 cycle. So that's exactly 1 cycle every 2 milliseconds, which is what it should be. Does that make sense, Gabe?
Yes.
Absolutely. See, even Gabe agrees. All right, this is easy stuff. Everybody get that? All right. So notice if we go back to our equation, we have 2 pi times t over tau. So t goes from, t is our time, and essentially t over big period, t over t, that's second over second, that's seconds over seconds divides out due to be just no units. And so this is you can see that this ratio here is a fraction of a cycle. It's either a fraction of, like, this could be 0.1, 0.2, a half a cycle. If this is 1, then that's that's t over t, which is 1, and 2 pi of 2 pi. And so this argument here is in radians. It's not in degrees. This is a key point. This is in the radians. Hopefully you've seen this before. And so this is all described here on page 1. All right. And okay. Gabe, does that sound right?
Sounds right.
Let me flip this over. All right, now we go to page 2. And in page 2, what we're going to do is we have our microphone set right here, and we're going to put the microphone into this tube. Let me put some duct tape on this. Okay, so notice, if you look on page 2 of the lab, the speaker, now the speaker is on the right-hand side, the microphone is somewhere in here, and as I slide the microphone back, notice that the speaker is making kind of a wave, a sound wave that's traveling through this tube, as represented by this sine wave here on the picture on page 2. As I move the microphone back, I'm moving the microphone through different positions on that wave. And so when you look at the bottom, if you look at the bottom signal that's coming from the microphone, as I move this microphone back, I can see that my relative position is going to shift. I can see that the relative position is going to shift. Ready? Let's see if it does. It's kind of jittery. Gabe, can you see that the relative position is shifting?
Yes, we can see that.
Okay. Now the amplitude is shifting, but that's because the microphone is getting closer to the speaker. Okay. Now, on page 2, what we're also going to explain that I can put the mic and I can put this oscilloscope in what's called XY mode. I'm going to, like this. And in XY mode, the oscilloscope just produces a single dot. And Gabe, can you see the dot right there?
Yes.
Now notice in the dot, basically channel A moves the signal up and down. Channel B moves the signal right and left. Okay? So if I control both of these, I can move the dot all over the place. It's kind of like one of those boards. It's kind of like an Etch-a-Sketch, right? Etch-a-Sketch, you know what an Etch-a-Sketch is? All right, so I can move this one horizontally, I can move this one up and down, and I can make the thing go in circles if I want to. Now, here's the tricky thing. The tricky part is if I now turn the signals on, I generate some kind of what's called a Lissajous pattern. And Lissajous is look on page, well, it's on page 2, but it's also on page 4. I'm going to flip over to page 4. What happens is it's kind of noisy, I grant you, but it's a Lissajous pattern. The idea is that I have 2 sine waves. The speaker is making the sine wave go up and down, or the speaker is making the dot go up and down, and the signal from the microphone is making the dot go back and forth. So because they're in phase, it looks like an ellipse, and the ellipse will change depending on the phase. Gabe, can you pick this up?
Yes.
All right. And if you flip over to page, well, there's page 3 of the lab, which explains more about this. Please read page 3. But if you look at also page 4, where we demonstrate that if the 2 signals are exactly in phase with each other, we get a perfect 45-degree line, like that. Okay. As they go out of phase, it looks more like an ellipse. If that becomes 90 degrees, it looks more or less like a circle. The 90 degrees out of phase. If they become more like 180 degrees out of phase, it looks more like a line, but the other way, going the other way. Does that make sense, Gabe? All right. So here's the idea. The idea is when we go a full, and I'm going to change to a higher frequency to make this more obvious. There we go. Kind of jittery, I agree. But we let it settle down. So this is almost 900 hertz, 899 or almost 900 hertz. And when I go from here, there's 90 degrees out of phase. That's 100. That's a half a wavelength. So the idea is so from here to here, that's a full wavelength. So when I start from here, where they're exactly in phase, and then I shift, whoops, this is noisy, to about 90 degrees and back, that's half a wavelength, and then I come back, and then all the way back to here, we have just gone a full wavelength. Does that make sense?
Yes.
Alright, so if we move back and forth a full wavelength from here to here, here's the idea. Gabe, are you getting this?
Yes.
Right here? Alright. We all have the idea, we all know X equals VT. We all know that equation. X equals velocity times time. Alright, so what we do is we let X be the wavelength. X is the distance of one complete wavelength. V is the velocity of sound. That's the actual speed of sound. And the time it takes to traverse one wavelength is the period. Now, the frequency is 1 over the period, right? So, that means that the period is 1 over the frequency. So if I put this V sound times 1 over frequency, I can do that. I'm substituting right here. Whoops. Right. And I'm going to multiply the wavelength times the frequency is equal to the speed of sound. So this is our fundamental equation here. So we measure the frequency. This frequency is 899 hertz. We measure the frequency, which is our frequency counter. This is a frequency counter right here that measures it precisely. We measure the wavelength by moving the microphone back and forth. We simply multiply the wavelength by the frequency, and that gives us the speed of sound. Does that make sense?
Yes.
Very cool. All right. So, Gabe.
Yes.
Here's what we're going to do. What is the temperature in the shed today?
Cold.
Cold. It is cold. Unfortunately, this is an unheated shed. Sorry about that, Gabe.
Ish.
Cold-ish. That's why, can you see our heater going?
Yes, I should just.
You should, okay.
Yes.
Would you say it's 60 degrees in here?
I'd be okay with saying it's 60 degrees.
Because I do not have, I do have a thermometer somewhere. Should I go get my thermometer?
Let's just call it 60.
We'll call it 60. Close enough. Alright, so our degrees is 60 degrees Fahrenheit. We'll have to convert that to centigrade. So Gabe, here's what we're going to do. How would you like to run this experiment?
I'd say I'm happy being the cameraman. Let's get the precise measurement that you want.
Are you sure, Gabe?
I'm sure.
Tell you what, I'll take a couple measurements, but then you take some measurements too. How about that?
Alright, sure.
We'll switch back. Alright. So the first measurement I'm going to do, I'm going to turn this frequency down to we're going to say it's 500, or really it's 499. So the first frequency is 499. Let's see if I can. Okay, I'm going to call that about it. That's about 52 and a half. We're making a measurement here, 52 and a half centimeters. It's about 90 degrees. I'm just going to go half a wave. Oh, problem is, I need to start again here.
You need to start again?
Sort of. I'm going to take the measurement right. We're going to start right here, 70, and work myself backwards. But I only went half a wavelength, so I really have to multiply that by 2. Does that make sense with me?
Yes.
So that means that wavelength, peak to peak for the full wavelength, is about 0.83 meters. 0.83 meters. Okay, at this point, I'm going to change the frequency to a higher frequency. Let's do that frequency. That's right at 800. That's 45.5. So I'm seeing where the reading right here at the edge of the PVC pipe, 45.5. Let's go for a full wavelength if we can. $90. It's 180. Let's start again. I'm going to take the measurement out here. I did 20 centimeters. $90 degrees. $180. Back to about 60.5. So 60.5 minus 20 is
40.
40.5.
40 and a half.
40.5.
40 and a half.
0.45. Alright, now let's change frequency. Okay. How about that?
Sounds good.
1200?
I mean, it doesn't really sound good, but
1198. Almost 1200. All right. Now, the higher the wavelength, the higher the pitch, the shorter the wavelength.
yes.
Does that make sense?
Yes, so this would be fairly short.
Okay, about there. And that measures 40.5. $69. Oops. 28.5. Does that make sense?
What was it? What were the two numbers?
69
69
minus 40.5.
minus 40.5 should be 28.5.
28.5. So 0.285. Okay, Gabe.
Okay.
Now you do it.
Okay.
We'll switch.
We'll switch.
All right. Go ahead and pick a higher frequency.
Yeah, so I'm just trying to find a higher. How about that?
Sounds good.
That's 1608.
Oh, here's your pin.
So the first measurement is maybe. We'll see. So that's right at 30.
Mm-hmm.